Example 113.5. In many sports, eligibility for minor leagues is determined by age at the start of the calendar year, January 1st. Journalist Malcolm Gladwell wrote about the effects of this eligibility rule on Canadian hockey in his 2008 book, Outliers. The issue is that people born in the early months of the year end up being older when they are finally able to participate in minor leagues than students born in later months. For example, a child born on January 2nd who is eligible to play when he or she turns 10 will be 10 years and 364 days old when he starts playing, compared to a child born on December 31st who will only be 10 years and 1 day old when he or she is eligible to play. Being older is an advantage in sports, so these older kids naturally perform better and stand out more to coaches and scouts. Stephen Levitt and Stephen J. Dubner, authors of the best-selling Freakonomics series of books, noted this trend in international soccer in a 2006 New York Times column. FIFA introduced a January 1st cutoff date in 1997. Of the 410 players in the 2006 World Cup born after 1979, the percentage who were born in January, February, and March was 32.4%. Use the 2006 World Cup data and a 99% confidence level to form an interval estimate for the true proportion of FIFA players born after 1979 that have a birthday in the first 3 months of the year. Assuming that for the general population, the birth rate for the months January, February, and March is approximately 25%, does it seem the proportion of FIFA stars born in these 3 months is significantly higher than the expected 25% rate? Okay, so it's kind of a long problem, right? A whole page to read through. What we want to do here is to identify through all those words what we're actually asked to do. And I think it's very clear. It says a 99% confidence interval level, right? To form an interval estimate for the true proportion of the FIFA players born after 1979 that have a birthday in the first 3 months of the year. So it's a confidence level, right? 99% confidence level. So that means we're going to be doing a confidence interval. And since it says it's for the proportion, we know it's a confidence interval for the proportion. So let's copy down what we know from the problem, right? N, the sample size in this problem. If we look back at what they gave us in the beginning, it says of the 410 players, right? So that's 410 for the sample size. Then it will give us a proportion, right? A proportion, a p-hat. It says of that, it says the percentage who were born in January, February, and March was 32.4%, so 0.324. Now from there, we're going to go further and look down and see that they give us a confidence level of 99%. So we'll need a q-hat, and we're going to need that confidence level. So let's write down the confidence level, 0.99. And then we can get the remaining two pieces from what was given. So the q-hat, which we don't have, and the alpha, which we don't have in the problem, can be obtained from the two things given. If you remember, q-hat is just the complement of p-hat. So all you have to do is take your calculator and subtract those numbers from 1. So we're going to say, starting with the, nope, my calculator is telling me I need more batteries, right? But 1 minus 0.324. And when you do that and hit enter, you get your answer for q-hat. So that's going to give us 0.676. And then we're going to do same thing for confidence level. Of course, that's 0.01. So those are your results for the data that we need for the confidence interval for the proportion. So the next step then is to come up with our critical value. Remember, for proportion problems, the answer is always z alpha divided by 2. Since we're using the bell curve to approximate the binomial distribution, we'll always use a z alpha divided by 2 value. Also, the sample size is always very large for these problems. All right, so z alpha divided by 2 for a 99% confidence interval, we need to go to our table and look up this alpha divided by 2. So we're going to be looking up 0.01 divided by 2. That's the same as looking up z 0.005. So in our table, we're going to go to the 0.005 row, and since we're looking for a z value on the t table, we're going to go straight to the bottom and find the number down there at the bottom. So let's go do that now, and we'll come back and fill in the answer. Okay, so we're looking up 0.005 in one tail and moving the table all the way down to the bottom where the z-scores are located. We find the answer to be 2.576. 2.576. Okay, so we found the answer 2.576 for our critical value. Our next step then is to plug that into our margin of error formula. So let's do that up here. The margin of error formula, remember, is the square root of, right? Actually, it's the critical value, z alpha divided by 2 times the square root of p hat q hat over n. So our z alpha divided by t value is 2.576 times the square root of our p hat and q hat multiplied, so 0.324 times 0.676, right? And then we'll divide all of that by the n, which is 410. All right, so you're going to take this value and eventually come up with e. So let's see what that gives us. Okay, so we have 2.576 times the square root of 0.324 times 0.676 divided by 410. Close up the parenthesis, hit enter, and we get our answer for E. It's basically 0.0595 ... I'm going to store it in my calculator so I have it for use later. So store into X, and then let's finish it up for our last step. So taking this E value that we found, we're going to now use that to form the interval and finish up the problem. So our interval will be p hat minus E, comma, p hat plus E, right? And when you plug in the p hat value here, it's 0.324 minus 0.0595 ... And you'll do the same 0.324 plus that error, 0.0595 ... And let's see what that gives us finally for our official interval. So we'll have 0.324 minus the error, and that'll give us for the first part 0.264, and then we'll do the same but this time plus the error, and we get 0.384. Okay, so there it is, and we'll finish with our classic statement, that we are 99% confident, right? We are 99% confident that the true proportion of FIFA athletes born in January, February, March is between, and the numbers they're between, of course, are 26.4% and 38.4%. Okay, so there's our interval, and there's our interpretation statement. The last thing we have to do is to see if we can make sense of the last question they asked us, which is to say, does the proportion of FIFA athletes born in the first 3 months of the year seem to be higher than what's true for the general population? Well, if we expect the general population to have a 25% birth rate in those first 3 months, then the question is this proportion interval higher than 25% in all cases? Well, if you look at every number in the interval, it starts at 26 and ends at 38. All those numbers are higher than 25%. So it means that no matter what the proportion is, if we believe it's in this interval somewhere, no matter what value it is in this interval, all those values are higher than the 25% rate for the general population. So it does seem that perhaps people playing in FIFA, or FIFA athletes who are the elite soccer players in the world, that those individuals might be disproportionately born in the first 3 months of the year, which means they could be benefiting from the fact that they're born early, and that means they're older when they start playing, actually, and that means that they're stronger and faster and all those things that come with being older as children. And so hence they get the better coaching because they get assigned to the all-star teams in their respective countries and their minor leagues, and then eventually, they benefit from all those years of better coaching and better training because some coach very young, very early on, deemed them to be better than everyone else. But really the reason why they might have been better was because they're just simply older and therefore stronger and smarter and more mature, etc. So in the end, this could be evidence to say that this effect is very real in the sport of soccer.